Good afternoon, everyone. Thank you very much for joining the session. I hope you had your great lunch. I can see from your face that you are fresh and you are ready to go on an OMP journey with me. So first, I will start with some housekeeping stuff. I will encourage you to join this WebEx space that is for our session. If you have any questions during the session, you can ask in the WebEx space. We have some moderators there that can answer your questions during the session. But I will make sure that we have enough time at the end of the session so that we can open up the for Q&A stuff. And that WebEx space will be active until 28th of February. So you can ask any questions related to your SD-WAN fabric or any issue you are facing. I am more than happy to help you. So I will start off my session by sharing this quote, which I really liked it. Someone says that it is associated with the Albert Einstein, but I was not able to verify it. But I really liked it. So if you cannot explain it simply, then you don't understand it well enough. So the key takeaway from today's session is that you understand the OMP so that you can scale your SD-WAN fabric. My name is Vakas. I am from Belgium, Brussels. I did my master's from KTH, Stockholm, Sweden. Then in 2011, I joined Cisco Tech Brussels. And after that, I moved into different roles in AS, where I support the SD-WAN technology. And right now, I'm working as a customer success specialist, covering SD-WAN and thousand-eyes technologies. So the agenda which we're going to cover today is being divided into 4 parts. So the first part is we will take off. We will start to understand what is OMP, how OMP pairing is being established, what are the different processes that is being involved on the SD-WAN edge devices and the controllers that build the OMP pairing, how the routing is being done, and what are the troubleshooting tools which we can use in order to troubleshoot if something happened in the OMP level. In the second part, we're going to talk about how the OMP best path algorithm works, how the loop avoidance mechanism that has been done in our in order to integrate different protocols in our SD-WAN fabric, and what are the enhancements that has been made in OMP from the past years that can improve the OMP protocol. Then we're going to talk about how the multicast is being built in the SD-WAN fabric, how the route is being built, what are the different messages that is being exchanged in order to build up that multicast tree. And then we're going to touch upon, we have a feature called service chaining that used OMP, and we're going to talk about how the service chaining is being implemented using OMP in the SD-WAN fabric. So before we start, so let's do a quick recap and try to understand, what is Cisco SD-WAN solution. So Cisco SD-WAN solution allows you to connect any user to any application with integrated capabilities of cloud connectivity, security, and enhanced network visibility. Cisco SD-WAN fabric is also called an overlay network that can run over any network transport, meaning that it is transport agnostic. And that overlay network is being built with the help of different controllers and the WAN edge devices. In Cisco SD-WAN fabric, we have 3 controllers: Cisco SD-WAN validator, Cisco SD-WAN controller, and the Cisco SD-WAN manager. Cisco SD-WAN manager is a centralized network management system that allows you to configure and manage the entire overlay network using the graphical user interface that Cisco SD-WAN manager offers you. It establishes secure channel or control channel, which can either be a DTLS tunnel or the TLS tunnel that is being built between the controllers and the WAN edge devices. And in order to communicate with the controllers and the WAN edge devices, it uses the netcon protocol inside that control channel or DTLS or TLS tunnel. And then we have a Cisco SD-WAN validator, which automatically orchestrates the connectivity between the WAN edge devices and the controller. And if any controller is behind the NAT, then the Cisco SD-WAN validator also acts as a NAT traversal orchestrator. Then we have Cisco SD-WAN controller, which establish a control connection, permanent control connection, DTLS tunnels or TLS tunnels, with every WAN edge device which we have in the Cisco SD-WAN fabric. and the OMP runs inside that control connection. So now we're going to talk about how this control connection is being built, right? So a Cisco SD-WAN manager and Cisco SD-WAN controller initially contacts and authenticate with the Cisco SD-WAN validator. Because these controllers can have multiple vCPUs or core, then each core will establish a permanent DTLS connection with the Cisco SD-WAN validator. So once the WAN edge device initially comes up and tries to establish a temporary or transit DTLS connection with the Cisco SD-WAN validator over each WAN transport that WAN edge device has, because SD-WAN controller can have multiple cores, and each core establish a permanent DTLS connection with the Cisco SD-WAN validator, right? Then the Cisco SD-WAN validator knows how many cores each SD-WAN controller has. So once the WAN edge device is trying to register itself or trying to establish a temporary DTLS connection with the Cisco SD-WAN validator over each WAN transport, then the Cisco SD-WAN validator send a register reply message back to the Cisco SD-WAN edge device. And in that WAN register reply message, it contains the list of controllers along with the cores that the Cisco SD-WAN validator selects. Once the WAN edge device receives that information, it mapped into that index. So once the WAN edge device receives that index of controllers along with the cores, then the WAN edge device randomly selects an index number and start establishing the control connection with that SD-WAN controller. And it depends how many control connection it has to establish. It depends upon the configuration which we have under the TLOC configuration of the WAN edge device. By default, it's 2, so it's tried to establish the 2 control connection. And if because I said that it is use a random value and it starts with index value. If the index value which is selected from the list is the end of the list, then it will move towards the start and then start establishing the control connection until it reach towards the maximum control connection configuration value which we have configured under the TLOC. So once the TLOC is being established, then the OMP, SNMP, and the netconf runs inside that control connection. So now we understand how the control connection is being established now. So now we're going to talk about what is OMP. OMP is a routing protocol that is similar to BGP that manages the entire overlay network. OMP runs inside the DTLS connection, which I just explained you. It uses TCP as a transport protocol, and it listens on port 17900. OMP runs in a client-server model, right? Cisco SD-WAN edge device act as a client, and Cisco SD-WAN controller act as a server. Like BGP, OMP supports both IPv4 and IPv6, and it also has a built-in loop avoidance mechanism, which we're going to talk about in our later section. So once the OMP peering is being established, right? So it distribute vRoutes, TLOCs, services, and the policies. So vRoutes are those routes which we learn from the LAN side of the WAN edge devices. So once we learn it, and then OMP will try to advertise those routes through OMP protocol, and when the WAN edge device advertise it, it attach different attributes with those service route. And those attributes is gonna used in the OMP best path algorithm. Then the OMP also distribute TLOCs, which are basically the WAN attachment points, like how many ISPs you have, how many links you have that you are using in order to connect with the ISP. And that TLOC is being identified with the system IP, color, the encapsulation, and it also have different attributes. Then we have services. So if you have any services which you introduce in your Cisco SD-WAN fabric, then the OMP is also used to advertise those services in the Cisco SD-WAN fabric. Then OMP is also responsible to advertise the policies, and these policies are basically the centralized data policies that is being used by the OMP protocol and sent by the controllers towards the WAN edge devices. So now we know that what is OMP, right? So now we're going to talk about how the OMP peering is being established. So OMP peering is being established between the system IP address of the peers. And because we already talked about that, like a WAN edge device can have multiple, control connection with the SD-WAN controller, right? So, but the OMP peering will only be one, which is run inside the DTLS control connection. If we have multiple TLOCs, means multiple WAN edge devices, multiple WAN edge attachment points on the WAN edge devices, right? And it establishes multiple control connections towards that SD-WAN controller, then there is only one OMP peering. And the benefit of having only one OMP peering is that once the OMP peering is being established, then the OMP peering runs inside that both of these DTLS connections, which is being established over that particular SD-WAN controller instance. And there is no configuration command at this moment right now that we can see which control connection is being used to see that the OMP peering is being established inside that DTLS connection. So if any of the DTLS connection that is being used to establish the OMP peering, it goes down, then the WAN edge device will automatically switch that OMP peering towards the next available TLOC, which establishes that control connection with it. Because SD-WAN controller or the OMP works in a client-server model, right? So it has to establish first the TCP connection, and after that, it starts exchanging the OMP packet to build up the OMP peering. Because SD-WAN, the OMP works in a client-server model, so the client acts as a TCP in TCP active mode, and the server will act as a TCP passive mode, meaning that the client will initiate the TCP connection with the server, and then it will send the OMP packet to establish the OMP peering. But I have already said that the OMP peering is being also established between the controllers, right? And if the OMP peering is being established between the controllers, then which one will be the client and which one will be the server? So the controller which has the lowest IP address will act as a client, and with the other one which act as a server. So now the OMP protocol has 7 packets which is being used to carry the routes, TLOCs, services, policies information. And we're gonna go each of these packets, how it is being exchanged, and what information it carries to build up the OMP peering. So first is, the first packet which is being exchanged is handshake. So I would like to give you an example related to Cisco Live, right? So you have already seen while walking in the corridors, right? You met some people, and first you try to make an eye contact, right? When you saw some old friend. So just try to think that the eye contact which you make with your peer or with your colleague is just like a TCP session you establish. And then you try to approach and you said, hello, how are you? How is your Cisco Live session is going on? So these are basically the OMP messages that you just exchanged. So the first packet is handshake. You approach them, you say, hello, how are you? And then you try to exchange this information, right? So once the TCP session is being established, the first packet which is being exchanged is the handshake packet that contains information about site ID, hold time timer, what are the capabilities that the particular WAN edge device can support. Once the handshake packet is being exchanged and the peering is being established, then we exchange hello packets. These are just the keep alive mechanism to see if the remote peer is alive or not. Then we have the update package. That update packet is used to exchange the routes, TLOCs, messages over the SD-WAN fabric. And if any TLOC is not available, then that update also being sent through that update packet. Then we have the query packet. And if you are doing any aggregation in your SD-WAN fabric, then the query packet is being sent by the WAN edge device to ask about if we have any more specific routes available in your SD-WAN fabric. And then we have this alert packet that is basically the just like the BGP notification messages, if any bad thing happen or if you are not able to receive the packet, the packet is corrupted, then the peer send that alert packet and gracefully shut down the peering. Then we have this inform packet. Inform packet is being used in an OMP graceful restart feature. So basically, when the OMP peering goes down and came back up, it will send the end of RIP packet just to flush out all those routes. So basically, this is just the inform packet that is being sent by the WAN edge router. And then we have this policy packet that is being used to send all those policies in your SD-WAN fabric. And those policies can be centralized data policy, application-aware routing, a policy which you configure for your SD-WAN fabric, or cFlow templates, etc., etc. So now we're going to see what are the different states we have while establishing the OMP peering. Every peer will start with an invalid state, meaning that it did not initiate the TCP connection yet. So once the TCP connection is being established, then it moves to the init state. And then it sends the handshake packet. If the handshake packet is OK, then it will wait for the remote peer to send the handshake packet. If the handshake packet is corrupted or is not being well received by the peer, it sends the alert message and move back to the init state. Then once we receive the handshake packet, we wait for the remote peer to send the handshake packet. When we receive the handshake packet, it is moved to the handshake confirm, and the peer comes up. And if anything bad happened, like the packet is corrupted and we were not able to read the packet or packet is lost, we send the alert message and we move back to the init state. So I told you OMP works in a client-server model. So if the OMP peering is being established between the SD-WAN edge device and the SD-WAN controller, who will initiate the TCP connection? Anyone? SD? Good. And who initiate the TCP connection will send the handshake packet. We receive the packet, and then we exchange the hello packets. And if the OMP peering is being established between the SD-WAN controllers, who will initiate the TCP connection? Sorry? Lowest IP. So 221.2.2.2 will initiate the TCP connection, sends the packet, handshake packet, receives the packet, and the hello packet is being exchanged, and then OMP peering is being established. So we talked about that. We exchanged the handshake packet, right? But there are some conditions that needs to be met so that the OMP peering comes up. The one is the domain ID needs to be matched. And by default in SD-WAN Fabric, the domain ID is always 1. Then at least one address family that peer supports needs to match, and the capabilities that is being mentioned in the handshake packet needs to match. If these conditions are met, then the peering will come up, and they will start exchanging the messages. If any of the conditions does not match, then we send the alert packet, and we gracefully shut down the OMP peering. But if the handshake packet is OK, right? But we exchange the hello packet, but during the hello packet exchange, we receive the hello packet, but the peer IP address does not match which we exchange in the hello handshake messages. Then after receiving that hello packet, we send the alert message back to the peer that I'm gonna shut down the peering because you are not the one which I exchanged the handshake packet. So these are the conditions which needs to met in order to establish the OMP peering. I talked about that OMP is being derived from the BGP. So there are some similarities which we have in the OMP and the BGP. I'm going to talk about that. So the BGP uses TCP as a transport protocol, and OMP also uses TCP transport as a protocol. BGP uses keep alive messages when the BGP neighbor is up. Same is the case in OMP. When the OMP peering is up, we exchange hello packets. BGP provides a mechanism to gracefully shut down after sending the BGP notification message. Same is the case, we have this alert packet. When the BGP converges, we only send the incremental updates towards the BGP peer, right? Same is the case with the OMP. Once the OMP is converged, we only send the incremental update towards the BGP or the OMP peer. in order to understand the OMP routing process, we just need to go back to the classic BGP routing process so that we can map to see what are the similarities we have. So this is the picture which I took from the Internet Routing Architecture, the famous book of the BGP from Sam Halby. So we have adjacent RIB. So these are the RIBs which we have from the BGP peer, right? We receive the routes. We feed that into that BGP decision process. We can also apply the input routing policy, like which routes we want to accept from that particular peer. Then we run the BGP decision process. Based on those BGP decision process, we select the best routes, we put it into the local RIB, and we apply the output policy, right? Which routes we want to advertise toward which peer, right? And those routes will be placed into the adjacent RIB out. So everyone knows that. Same is the case we have with the OMP, right? We have separate RIB in for each OMP peer. We have a separate RIB out for each OMP peer. However, because OMP supports multiple address families, right? So each peer RIB in also have a separate RIB in for each, the TLOCs, the address family that OMP protocol support. Another important thing which you need to understand is that, so we receive the routes from the OMP peer, we apply the input routing policy, or the control policy, that based on that will be feed into the OMP decision process, right? So whatever route we receive from the OMP peer will be placed in the RIB in, and those will be, calculated in the RIB in scale of that SD-WAN controller. But if we have the output policy applied and we reject those routes which we received on the RIB in, then the RIB out will not be generated, right? So the scale point of view, whatever routes you receive from the WAN device will be placed in the RIB in. That's very important to understand. So these are the address family which OMP protocol support: TLOC, vRoute, multicast services, etc., etc. So this is what I just explained to you. These are the key points. We have a separate RIB in and separate RIB out for each OMP peer. When we apply the control policy, it is before the OMP decision process works or the kick in. And if we reject any routes in the RIB in, it means that it will be placed in the RIB in of that SD-WAN controller, but the RIB out will not be generated. However, when we accept the RIB in routes which we receive from the peers, we accept it in the RIB in, and OMP select those routes. And in the outbound control policy, we reject the routes to be advertised to that particular OMP peer, then the RIB out will not be generated. So that's very important to understand. So this is just, the graphical. We have our RIB in for just each peer, and we have a separate RIB in for each TLOC that particular peer RIB in supports. So I just explained, how the RIB in and RIB out works, So let's take a quick demo, right? So we have three sites, site 110, site 111, and site 112. And we have these 4 prefixes on each site. And our intention is that just to simulate how the RIB in and RIB out calculation works, is that whatever the first 2 routes from site 110, we just want to reject it and see what is the impact we can see on the RIB in and RIB out calculation. And the second policy which we applied on the outbound direction, that first 2 routes which we received from the site 111, we don't want to advertise it into the site 112, right? So this is the control policy we have. So this is on the inbound direction, right? We receive the routes. We receive the routes from site 110, from VPN 10, and this is the prefixes. Or these are the 2 prefixes which we try to block receiving from the site 1110. And this is for the outbound policy, which we match the route from site 11 and from VPN 10, and we don't want to advertise it into the site 112. This one. This is the outbound policy direction. So before applying any control policy, we can see that, right, or we are receiving all the routes from every site. We can see that in the output, like we have this 10.10.1.1.2, we are receiving that. But as per our control policy, intention is that we just want to block that. So once we apply that policy in the inbound direction, we can see that these routes are in reject state or invalid state, right? So when we see that command show like whether these routes are being advertised towards the other peers, we can see that 10.10.10.3, that is the only routes which we receive from the site 111 is being advertised to all the peers, but the first two prefixes are being blocked. So when we check the OMP rib, here we can see that the routes are still being placed in the rib bin, but the attributes which are associated with that particular prefixes is being rejected and resolved. So the prefixes which we received, if we reject it, it will place in the rib bin. And if we check this for the routes which we want to advertise or which we accepted in our policy, right? So we can see that the ribbon is being generated for that 110.3. So the two ribbons are being generated. So the first two ribs are the ribs generated for the WAN edge device 10.1.1.1.110, and then we have two controllers. So these are the reflected routes which we receive from the SD-WAN controller. And here we can see that we are creating the rib out routes for the prefixes which we accepted for every peer that WAN edge device has. Then for the outbound control policy, we just want to block the first two prefixes from the site 110 with 10.10.111.1 and 2. We don't want to advertise it to site 1112. And here we can see that these prefixes is being assigned to everyone except 1112. So we don't see 111.112 for first two prefixes, and for the 10.10.111.3, it is being advertised to 1.1.1.112. So here it is, we can see that from the ribbon perspective. So the prefixes is being for that particular peer 1.1.1.112, we don't create any rib out. We only create the ribbons which we accepted from that particular peer. And for the prefix which we are advertised towards that peer, we can see that the rib out is being generated for that particular prefixes which we allowed in our policy. So rib out is being generated and it is being advertised to that particular peer. So I hope it is clear to you that, because it is very important if you have a very large SD-WAN fabric and you want to see how you can scale up your SD-WAN fabric, how many routes you want to advertise, whether those routes will be placed in the ribbon and rib out or not. So now we're going to talk about the similarities in terms of packets we can have with the BGP, right? Because we say that the OMP is being derived from the BGP. So in the BGP, we have marker, length, and type. Everyone knows that. So we have a 16-byte marker type field, and then we have 2-byte length field, and in the type we can have open, update, and notification, and keep alive. Same is the case with the OMP. We have a marker, length, and type, and the type can be all those packets we just earlier, that the handshake, update, and alert. This is for the open packet. We have version, autonomous system, and in the handshake packet we have version, site ID, domain ID. Domain ID is always one. Then the hold and timer, peer router ID. These are the fields which we have in the open OMP handshake packet format. Then for the notification packet, we have error code, subcode, and the data which is related to that particular error. Same is the case which we have in the OMP alert packet. So now we're going to talk about how the policies is being sent through OMP into your SD-WAN fabric. And we already talked about we have a policy packet that is being used in the OMP protocol. So the OMP policy packet looks like this. We have a 1-byte type field and then the variable length data. So the maximum policy packet size can be 4,000 bytes. And the type field can be policy complete, start, more, and then delete, right? Because we use TCP as a transport protocol, so we need to extract that 20 bytes of TCP header, right? So the maximum policy packet size can be 3980. And if your policy is big, then it needs to be fragmented, right? So the first packet which is being sent by the controller, the type field will be policy start, and the subsequent fragments will have policy mod in the mode, and the last one will be when the last fragment will be sent, it will be policy end. So now we're gonna talk about the OMP peering discovery, how it is being done in terms of the process level which we have on the WAN edge device and the SD-WAN controller. We have different processes or many processes running on the SD-WAN controller and the WAN edge device, but I just listed the one which is very important for the OMP peering. So VDaemon, probably you have already know that, is the process which is responsible to establish the DTLS and the TLS tunnel. So once the SD-WAN validator sends the list of controllers along with the core, right, it is handed over to the VDaemon process. VDaemon process will establish the DTLS tunnel with the SD-WAN controller. Once the tunnel is being established, information is handed over to the TTM process, that is Tunnel Table Manager. So once this information is being populated, then the OMP process will extract the system IP information from the TTM process and it start establishing the TCP session between the OMP process running on the WAN edge device and the SD-WAN controller. Because OMP runs inside the DTLS control connection, so all that TCP session or the packet which is being sent by the OMPD process are in the clear text inside the WAN edge device and the SD-WAN controller. But when it handed over towards the VDaemon process, it is being encrypted, and then it will be sent inside the DTLS tunnel. The remote peer received in the VDaemon process, decrypted it, handed over to the OMPD. And if we need to send any policy information, same as the process, it is being sent in a clear text, handed over to the VDaemon process encrypted, handed over into the DTLS tunnel. Remote peer received it, handed over to the OMPD process after decrypting it. So that's how the OMP peering or the policy is being sent. So now we're going to talk about like how the SD-WAN OMP peering topology built by running some debugs, right? So this is the reference topology which I'm going to use, and my focus will be the Cat8KV10. And in our topology, I have 3 controllers, controller 1, controller 2, and controller 3. And system IP is 2.2.2.2. Controller 2 has 3.3.3. And the commands or the debugs which I'm using in this topology is based on 20.15.1 or 17.15.1. And so in order to see the messages that is being exchanged through OMP, right, we need to enable some debugs. So in order to run some debugs on the WAN edge device, you need to enable this debug platform software, SD-WAN OMP packets, and you need to put in the double quotes, right, which direction you want to capture the packets, what type of packets you want to capture, whether you want to capture the packets for all the peers which that WAN edge device is trying to establish or receiving the information, or you want to filter it out for that particular peer address. Once you enable these debug platform software, these debugs will not be listed or shown into these when you run this show debug, right? Because these debugs is run into the SD-WAN code of that WAN edge device, right? So show debugging only show the debugs which we enable it or which we run it into the IS portion of the code of the WAN edge device. So I have already explained to you, you can set the direction, either both received or the send, or what type of package you want to receive. So starting from 17.12, need to enable the traces along with the debugs you enable on the WAN edge devices. And how you can enable the traces, you can use these commands. So by default, these traces are set on a notice level, right? So meaning these traces will not show any logs into the traces, but once you change it into the verbose mode, then all the traces, all the log messages related to that OMP process will be listed there. And how you can, once you enable those OMPD traces along with the debug, you can run that command show logging process OMPD internal, and then you can see all those messages that is being exchanged. And how you can enable it on the SD-WAN controller, those debugs. So it's very simple, debug OMP, and then you can specify whether you want to see the policies messages being exchanged, or you want to see the packets you want to exchange between the SD-WAN controller or the WAN edge devices. Once you enable the debug, there are two files. Either in some version, the logs will be written in the var log temp log vdebug, but in the latest one, it is var log vdebug. So once you enable it, you can just do tail F, and then you can see all those logs will be printed there. So here in this example, I just enable this debug, specifically filtered to that 2.2.2.2, and then I enable that traces also. And here we can see that like once you enable the debug, you can run that command, and you can see that like the debug is being enabled in both direction, and I enable all the packets, right? So here we are just trying to see the log messages which is being exchanged between the WAN edge device and the controller, right? And here we can see that we enable these debugs on the WAN edge device. And we can see that the peer 2.2.2 is passive because it is working, it is acting as in a server mode. So the WAN edge device is acting as a client, so it will initiate the TCP session. So here we can see that try to active connect to 2.2.2, and then once the TCP connection is being established, it says that it is being established, and then we send the handshake packet. We specify what are the capabilities we can exchange. Then we receive the handshake message from the peer, and then hello packet is being exchanged, the peer comes up. Once the peer comes up, all those routes will be exchanged, and in order to see what routes we received from the vSmart controller, we can run that command show platform software SD-WAN OMP peer. Here we can see that what is the source port that the WAN edge device is trying to use in the TCP connection, like what are the capabilities that is being exchanged, what are the graceful timer we exchange between the peers, what are the T-logs which we send, how many routes which we receive, how many IPv6 routes which we receive. All information is visible in that output. And if you need to see the policy packets, you need to just enable these traces for that policy packet for the OMP. So once you enable those traces, make sure that you put it back into the notice level. So here we can see that the policy which I'm trying to push is the size of that policy is 14,085, right? So it is exceeding the policies, the maximum policy size packet which OMP protocol support is 3980. So it is exceeding that size. So it do the fragmentation. So it create the 4 fragments. So the first fragment is being sent with the type value start, then the more packet is being sent, and the last packet which is being sent with the type value set to end. It means that the policy is being sent successfully. Same is the thing you can see it on the WAN edge device. You need to enable these traces and the debugs, and then you can see that messages also. If you can also see that, like for example, if you apply the policy, you can run that command to see if the policy is being applied correctly or in the right direction for that particular peer. You can run that command show support OMP peer IP address on the controller to see that like which policy is being applied to that particular peer. You can also get that information to go log in into the vManage, but it is we are old people, so we like to run that CLI commands. So on the controller, when you do that OMP peer detail, here you can see that this policy sent and the policy received is that these counter is not being incremented or is not being populated. The why? Because the policy which we applied is a control policy. So the control policy is being executed on the controller. It is not sent to the WAN edge devices. So the policy which is being sent through OMP, then these counters will be incremented. So now I would like to ask one question, right? So for example, can someone tell me this policy received packet, why it is 12? Because in the previous log output, we can see that we send 4 fragments. So why it is 12? Yes? Correct. So because we have 3 OMP peering, here you can see that. We have 3 OMP peering, so 4 fragments. So these fragments will come from the 3 different peers also. So that's why we saw that we have 4 multiplied by 3 is 12. So we see that like we have the total packet received is 12. Then we also these just like the how many hello packets that the policy send, all those counters. And then we can see that the TLOC send. So this device has 2 TLOCs, but it has 3 OMP pairs. So it has to send the TLOCs to all the OMP pairs which that WAN edge device is having the connection with. So that's why it is 6 TLOC sent. So the TLOC received is 12. Because we have 6 WAN edge devices in our fabric, so 2 TLOCs on each device. So we have 6 multiplied by 2 is like 12 TLOCs which we received. Sorry? Sometimes when I was catching, so it takes some time, to process that packet. So that's why the counter is not matching. So how we can see that, like if its policy is being applied correctly, you can run that command and you can see that like on which peers you applied that policy, in which direction you applied that policy. So right now we have seen that the OMP peering is up. What if our OMP peering is not coming up? Do we have to worry? What are the troubleshooting methods we can adopt in order to troubleshoot that issue? So first thing first, right? So OMP peering runs inside the control connection. So you need to make sure that the control connection is up. If the control connection is not up, then it means that the OMP peering will come up. If the control connection is up, but still the OMP peering is not coming up, because the OMP peering runs or established between the system IP address of the peer. So we need to make sure that the system IP address is not duplicated across your SD-WAN fabric. If it is the case, then the OMP peering will not come up. We have also seen in the field, because I came from tech and I also have working with the different customer. Sometimes OMP process crash, but if it happened, then the OMP peering also does not come up. Then we need to engage the tech to see why the OMP process crashed, if the process is not being started correctly, and what are the next steps we need to take. So then we need to reach out to that. Reach out to tech to provide that information. But in order to see if the OMP process is being crashed, we can run these commands. We can also have seen in the field that sometimes the memory leakages happen for that OMPD process. So we need to see that if the OMP peering is not coming up, whether there is a leakage with the OMPD process, we can run that command to see what is the memory utilization of that OMPD process. So these are just the show commands just for your reference. You can use that later. If, for example, previously we discussed that the OMP peering is not coming up. But in OMP protocol or in our Cisco SD-WAN solution, if the OMP peering is up, but it went down, right? So we have a feature called OMP graceful restart, right? So what it does, so if the remote peer goes down, then we move into the OMP graceful restart mode. It continues operating the information which we received from the peer before it goes down. and it uses that information in order to communicate with the, to decrypt the traffic, right? It holds that information until into your cache until the graceful restart timer is being expired. Once the graceful restart timer is being expired, then we flush out all the information which we learn from the peer or which we hold it into the cache, and then then we need to wait for the OMP peering to come up. But during that OMP graceful restart timer, we continuously checking that if the OMP peering is alive, it came up or not. If it came up, then we immediately, flush the information which we stored in the cache, and we try to get the updated information from the OMP peer. Because OMP is also used to distribute the security keys, right? And during that graceful restart timer, right? So it also helps us to continue to operate in the data plane level, because the data plane also encrypts the traffic when it tries to communicate with the remote managed devices. So for example, in the OMP, we received the encryption key from the controller, right? The controller is lost, and you know that like once we receive the key, after 50% of the key time is being elapsed, we have to refresh the key, or we have to ask for the new key, right? If the controller is lost, then the graceful restart timer kicked in. We continue using the key which we have received previously, and we're using that key to encrypt the traffic towards that remote managed device. And then when the key is expired, then the tunnel goes down because we don't have any key. But during the graceful restart timer, we still continue transmitting the traffic which based upon the key which we received before the peer goes down. What if the graceful restart timer is being turned off? So as soon as we lost the control connections with the controller, all the tunnels will goes down. And it is not recommended, but you need to make sure that the graceful restart timer which you configured, it should be, the rekey timer should be twice the graceful restart timer. So here, all the control connections with the controller goes down, and we can see that the number of vSmart is 0. So all the BFD session, the IPsec tunnel went down. The other thing which we need to remember is that we can change the graceful restart timer also. But the change which we made on the controllers will be reflected on the WAN edge devices and vice versa. So if we change the timer on the controller, that is the graceful restart timer will be applicable on the WAN edge device. Here, in this example, we change the timer on the controller, and here you can see that it is being applied on the WAN edge devices. And if we make any changes in the graceful restart timer, then the OMP peering will be reestablished because we change it, and in the handshake packet, we can see that the graceful restart timer has to be negotiated between the peers. So now we're gonna talk about how the OMP best path selection process works. Before I'm gonna talk about this, you need to remember, or you need to memorize that, right? So the same picture which I just shown you, we have a ribbon. We receive for each ribbon peer, we have a separate ribbon for each address family that the peer supports. Then we have this control policy which is being applied on the inbound. Whatever policy decision you configured in the inbound policy, that routes will be placed in the ribbon. Then the OMP decision process kicks in. Based on that, we applied the outbound control policy, and the rib-out policy is being generated for that particular peer. So the inbound control policy, we restrict those routes based upon the inbound control policy. And the information which we get into the OMP best path selection process is that we need to make sure that the TLOC is active, meaning that the data plane for that particular prefix is active. If it is active, then we need to make sure that the routes which we are feeding into that OMP best path selection process is active route, not the stale routes, not the routes which we learn or which are in the graceful restart mode. we prefer the active route instead of the stale route, we prefer the lowest administrative distance. The routes which we learn from the peer, it has to be at the lowest administrative distance. We prefer that the route preference, we prefer the OMP which have a high route preference. Then the next step in the OMP best path selection process is that the TLOC preference should be high. And after that, we has to be the OMP with the best origin type, then the origin metric, and after that, it is the best path, best prefixes will be placed in the ECMP, equal cost multipath. If still the OMP process is not decided which routes to be selected, then we go to the next step. We select the routes which are not the reflected routes, meaning that the routes which we learn from the WAN edge devices instead of the routes which we learn from the controller. And then we check that if the routes which we received have the lowest system IP, or if the system IP is also same, then we check that which system IP have the private IP address of that particular TLOC, then we select that one. And once all the steps is being processed and we select the best path, then based on that, if we applied any policy in the outbound direction, we use those set of prefixes which we selected based upon that OMP best path algorithm. We feed that into that outbound control policy. If we configure any send backup path, we also send the backup paths in order to, if we have any failure, then we have to fast convergence for that the WAN edge devices. And then we also have this. This is just for your reference. I just created for the MRF because most of the customers are also using MRF or are moving towards the MRF, so that you can understand how the OMP best path selection algorithm works for the MRF. So now we're going to talk about how the loop avoidance is being done in the OMP. By default, OMP loop avoidance is being run through the system IP. And if the OMP interacts with the different protocols, for example, OSPF, EIGRP, RIP, we have a built-in mechanism that is being used to avoid the loops while the OMP is interacting with these protocols. So in OSPF, we have a down bit mechanism. So once we receive the routes from the controller and we redistribute into the OSPF, then the WAN edge device sets the down bit flag, so that when the WAN edge device will advertise the LSA updates, because in the LSA updates, the down bit is being set. So when the remote WAN edge device in the same site receives that LSA update, it will not install it because it has the down bit flag set. It will prefer the routes which it learned from the OMP. In EIGRP, when the routes is being redistributed from the OMP into the EIGRP, then the WAN edge device sets the external protocol field set to OMP agent, meaning that these routes is being learned through OMP. So when the EIGRP update is being sent towards the LAN site and goes towards the other WAN edge device in the same site, and it found out that the external protocol agent is set to OMP agent, then those updates will not be preferred. It will prefer the routes which it learns from the OMP. In RIP, same is the case. When the RIP is being redistributed from the OMP to the RIP, then the tag will be assigned into the RIP update, and that tag value is 44270. That is not configurable. It is in the code. So once the routes will be, RIP updates will be sent towards the WAN edge device, it finds out that the tag is being associated in the RIP update. It will ignore that. It will prefer the routes which it learned from the OMP. From the BGP, when the routes will be distributed from OMP into BGP, then this SOO, site of origin community, is being set towards the site ID, when the BGP update is being sent from the LAN side, it goes towards the other WAN edge device on the same site ID. It sees that the SOO community is being set to that site ID. It matches with its own site ID, so it ignores that BGP update, and it will prefer the routes which it learns from the OMP. So, yes.
Is the site of origin default mechanism in Catalyst SD-WAN, or it will always set it, or we need to get it enabled actually?
So the question is that the site of origin is it is configurable or not, or it is automatically set it. So once you enable that, once you try to redistribute that, that SSO will be automatically set to the site ID that WAN edge device has. So you don't need to configure it manually. You just need to make sure that you enable the extended community in the BGP configuration. So this is just the simulation. We send the prefix to the WAN edge device, WAN edge from the OSPF to the OMP. It goes towards this advertised into the SD-WAN fabric, and the CH2 receives that OMP update. We configure the route policy. We redistribute from OMP to the OSPF. This OSPF will be sent to the branch LAN, from branch LAN to the CH3, and from CH3 we can see that this down bit flag is set. So these routes will not be preferred. So the routes which is being received from the OMP will be set. And here we can see that the packet capture is being set. The down bit is set. And we can also see that, like in the debug logs, so we are discarding that LSA update because the down bit is set for that particular OSPF. From the EIGRP, we announced that prefix is CH1. We advertise it from EIGRP to the OMP. OMP distribute into the SD-WAN fabric. CH2 sees that, like, when we try to capture it, the external protocol ID is set to unknown because there is no dissector for the Wireshark to display that information. But when these from OMP, we redistribute into the EIGRP. The EIGRP update is sent, and here we can see that, like in the output, that the external protocol is OMP agent, so it discard that, and it will prefer the routes which it learned from the OMP. So once the routes which it learned from the OMP and the OMP peering goes down, then the routes which he learned from the branch LAN side will be installed. But the administrative distance for those routes will be 252. So that is very important. So the routes which we learn from the OMP will be preferred, but once the OMP routes will be discarded or the flush, then we prefer the routes which we learn from the LAN side, but the administrative distance for that prefixes will be 252. Same is the case with the RIP. We advertise it. We redistribute from the OMP to the RIP, and the tag is being assigned 44270. It goes there because SD-WAN, that tag is set to the 44270. It discards that update, and once the OMP routes will goes down, then the RIP will install those prefixes with the administrative distance of 252. For the BGP, same is the case. We redistribute from BGP to the OMP. We advertise into that SD-WAN fabric. From there, we say that when we distribute from the OMP into the BGP, the extended community is being set to the site ID. Then the BGP update is being sent. It reaches toward the CH3. From CH3, we can see that it is preferring the routes which it learns from the OMP, and the administrative distance is 251. So once the OMP goes down, then it mentioned that the SD-WAN down flag in the output. It means that the routes which it learns from the OMP is not available. So now it prefers the route which it learns from the LAN side, and the administrative distance is set to the 252. So now we're gonna, yes.
It wasn't about that, but I saw that you had the BGP AS numbers.
Yeah.
Were the same on the top floors and in between the different ones? How do you do that? Do you do some BGP loop avoidance thing, or?
No, just for the lab, I just set it for the same.
So it will work to have
Yeah.
you don't have to have different AS numbers.
No,
AS
no, no.
somewhere? Okay.
Same.
Okay.
Yeah.
Hello. Yeah, on the same topic, I wanted to ask about that the BGPD community tag assigned is based on the site ID, right?
Yes.
So if we have a service side connection to another site where we are doing the BGP from OMP redistribution and that BGP also talks to this site, is there any way to prevent those routes getting back into OMP?
Then you just need to use the filtering mechanism which the BGP has so that those routes will not go over that LAN side towards the other. So it will not feed back to the SD-WAN fabric.
Yeah, but the other problem which I'm running into is the routes which are coming in from the other service side, which is learned over OMP on another side, is preferred on that SR or C edge over OMP route because of the AD. The AD coming in is 20 and then OMP is 251.
Yeah.
So how can I avoid that? I mean, I want to have that as a backup route, but I want to still prefer OMP.
Can we discuss
Yeah.
it later, right? So
Yeah.
I need to finish some, and then we can have this question. So now we're going to talk about what are the enhancements which we have in the OMP in the past releases, right? So if we have any outbound control policy which you applied in your SD-WAN fabric, and that control policy is being associated with the different peers, meaning different WAN edges in your SD-WAN fabric, right? Before 20.10, it is being evaluated against each peer, so it caused lots of CPU cycles from the OMPD process level. So now the enhancement which we have made in 2010 is that, so once that control policy in the outbound direction is being applied or it is being evaluated for one peer, it is being cached, and if the same sequence of the same policy is being used for the different peers, instead of re-evaluating that policy again and again, we use the information from the cache and we just apply that. So that feature is always enabled in 20.10. So that is outbound policy cache. So how you can see that? So once the policy is being applied to the one peer, and we can see that output or that result is being cached in the RIP. And once these policy is being applied to another peer, the information we get from the cache, and then we can have a less CPU cycle from the OMPD process level. The other enhancement which we have in the OMP is that we don't face any TLOC flaps, right? Our SD-WAN fabric is very stable. Yeah? Okay. No, it's not the case. In real world, we see flaps. So the enhancement which we made in 20.9 is that all the TLOCs which is being used in all the control policies on SD-WAN controller, those TLOCs will be placed in a list. If any TLOC that is not in that interest list, then are not experiencing the flapping, then the Cisco SD-WAN controller does not have to re-advertise those routes based upon the available TLOCs. That is one enhancement. But we need to improve that, right? So we make another enhancement which comes in 20.10, meaning that in the network, we have seen that the customer applied different control policies for different sites, right? So we create the interest list only for those TLOCs which is being applied into that particular control policy. We put it, and we does not re-advertise if the flap is happening outside that interest list to that particular sites. So these are the two enhancements that has been made, and these are the internal one, right? So you don't have to, do any configuration knob in order to enable it. So now I'm gonna do a quick demo about, like how the So we have these sites, right? So I can do a quick demo, right? So we have these 3 sites which are right now connected in a full mesh. And my intention is that like we want to have 2 hubs, EMEA Hub 1 and EMEA Hub 2. EMEA Hub 1 will be the preferred one, and the EMEA Hub 2 will be the, the in a standby mode. So when the EMEA Hub 1 goes down, then the traffic will be shifted towards the EMEA Hub 2. So now we can see that how it is being done. So here we can see that like we have this. So we have this. Wait. So EMEA Hub 1. Here we are just trying to enter. Here we can see that we have this VPN 10. VPN 10 is assigned with it 192.168.110.100. And then here we can see that we have a full mesh connectivity with all those sites in our SD-WAN fabric. We have the connectivity with the 10.0.0.2 and 10.115. And in this on this WAN Edge 7, which is that device, which is on site 1220. Here we can see that it is also have a full mesh connectivity, and we are receiving all those routes from all the sites. And now we are applying this control policy, which will do our intent to make the EMEA Hub 1 as an active one and the EMEA Hub 2 as the backup one. And here we can see that the EMEA Hub 1, we set the preference 20, and the EMEA Hub 2, we set the preference 10, and we block all those routes from being exchanged between the spoke sites. We only accept the routes which is being sent from the data center. So here we just enable the debugs, OMP events, best path, packet for all type of packet for that 10.1.1.7. I just want to narrow down it to one particular site. And now the policy is being sent, and here we can see that we are just sending the update message, because I mentioned that right earlier that the update message also contains the TLOC information. So here we can see that this one, MPLS IPsec 10.0.0.1, we set the preference value to 20, and we are sending that to the 10.1.1.7. And then for the other one, we also sending for LT, because we have 3 TLOCs, and we are sending setting the preference for 10.0.0.2. Here we can see that, and then. Here we are just sending the updates that these routes will not be available for you guys because as per our policy, we don't want to advertise the spoke prefixes to the other spokes. And here, because here you can also see that the feature which I just explained to you, that like if the policy is being applied in the outbound direction, right, and it is being placed in the cache, and here we can see that it is being hit from the cache, and it is using the results which is being stored in the cache for that all the prefixes. And here we can see that we are receiving the default route from, and it is being advertised towards that all the spokes, and like 10.1.1.5 and 10.1.1.6 and 7. And we receive the default route from 10.0.0.1 because this is a preferred one, default route which we want from the EMEA Hub 1. And this is the output which we run on the WAN Edge 7, and here we can see that we are receiving the routes from the controller 2.2.2 or 3.3.3, and we prefer the route from 10.0.0.1 and which is being installed. Yeah. So now we're going to talk about the SD-WAN multicast. And in SD-WAN multicast, these are just the terminologies. RP is the root. We have FHR, where the source is. Then we have LHR, where the receiver is. IGMP protocol is being used to ask that I am interested in that particular stream. Then the PIM is being used to exchange the PIM messages. And once we enable that OMP, once we enable the PIM on the WAN edge device, so the WAN edge device sends the OMP multicast auto discovery message towards the SD-WAN controller that I am PIM enabled, right? I am interested to be part of that multicast tree. So once that OMP multicast auto discover message is being received by all the WAN edges which are PIM enabled, the SD-WAN controller sends that multicast auto discovery message towards all the WAN edge devices in the SD-WAN fabric. So multicast auto discovery message contains the information which WAN edge devices are PIM enabled, which WAN edge device is the replicator, and what are the GPS coordinates for each WAN edge device is being has in order to when the multicast auto discovery message is being sent. So the classic flow of SD-WAN multicast control packet is that source registered itself to an RP, right? Receiver sends its interest to IGMP protocol that he wants to join that particular stream. Then the WAN edge device sends the *G join, and the first join will send towards the SD-WAN controller. From SD-WAN controller, it goes to the replicator. From replicator, it goes towards this RP, and from RP, it forwards it to the source, right? So once the source has that information about the PIM join, then the receiver send that S(G) join also. Then that S(G) join will be sent towards the SD-WAN controller, from SD-WAN controller to the replicator, and then the stream will start. But in SD-WAN multicast, the stream will never goes through the SD-WAN controller. It always goes through the replicator. So what are the OMP messages that is being exchanged? We have 5, 6, and 7. Right? And 5 is when the source is active in the SD-WAN fabric. 6 if they are interested to join the shared tree. And the 7 message, OMP type 7, is like when they want to join the source tree. So how does it happen? So IGMP receiver is interested to send that, like I want to join that particular stream. It sends the IGMP packet. It reaches to edge 2. Edge 2 sends that I received the IGMP request. It translates into the OMP type 6, that is shared tree message, like I want to join that particular stream. It sends that message to the SD-WAN controller. From SD-WAN controller, that type 6 message is being forwarded to the replicator. And from replicator, it forwards it to the edge 3, and because in our case, the RP is behind the SD-WAN fabric. It's outside of the SD-WAN fabric. And in this topology, we are using static RP. So every WAN edge device is configured with the RP information. So once the PIM join type 6 packet is being received by the replicator on the edge 3, edge 3 will send the PIM join *G towards the RP. And once the source tries to send the traffic over that particular multicast group, then the multicast traffic is being sent. Then the FHR will send that PIM register packet and register itself towards the RP that I have the traffic for that particular group, for that multicast. Then the PIM register message is being sent from edge 3 towards the RP, and then the RP already knows that I have a receiver that is interested to that particular stream. It sends the PIM join S(G), and then once the edge 3 will receive the PIM join S(G), it sends the OMP type update packet 7, which is S(G) means share. He wants to join the shared tree, shortest path tree, and then it sends that to the SD-WAN controller. From SD-WAN controller, it goes back to the replicator. From replicator, it sends the type 7 packet back to the FHR, to the source. Once the source knows that, like, I have the receiver, so it sends the type 5 packet back to the SD-WAN controller. It informs the WAN edge devices in the SD-WAN fabric that we have a source that is transmitting that stream for that particular group. So once the SD-WAN controller receives that information, SD-WAN controller sends the type 5 SA packet back to all the WAN edges that are payment enabled in the SD-WAN fabric. So now every WAN edge device knows that like we have a source available in the SD-WAN fabric for that particular group. So if then the traffic is being traverses from replicator towards the LHR and goes back to the receiver. If any other receiver comes in and wants to join the SD-WAN multicast traffic for that particular group, which that source is already transmitting the traffic, it sends the IGMP join. Edge 6 sends the type 7 packet because it already knows that who's the source, right? So it sends that packet back to the SD-WAN controller. From SD-WAN controller, it sends the replicator B because edge 6 is closer, it chooses that replicator B because it closes close to that replicator B because when the OMP multicast auto discovery packet is being sent, it also contains the GPS information, and that GPS information will be determined which replicator I have to select, which is closest to me. So then those messages will be sent to that replicator. So the type 7 message is being sent to the replicator by the controller, and the replicator sends that type 7 message towards that FHR. From FHR, it goes to the source, and then the multicast stream traffic traverses from the replicator and goes to that particular receiver. And these are all the steps which are just simulated in that simulation. These are just for your reference.
Can we have any cast RP or?
Sorry?
Can we have support of any cast rendezvous point?
Which rendezvous point?
Anycast.
Anycast, yes. This example is for the Anycast rendezvous point. So the question is like if we can have Anycast rendezvous point. So I just explained that the example which I just showed is just for the Anycast rendezvous point. So auto RP is just, so the messages will remain the same. These are the OMP messages, but the RP selection is just for the auto RP, just for the RP selection. So they just exchange automatically will select that. So the selection of the replicator is just solely based on the from the receiver point of view. It doesn't have to go do with the source. And if we have multiple replicators in your SD-WAN fabric, there is no synchronized mechanism between the replicators. So if any case the replicator goes down and you are using that replicator to receive that stream, then there is some glitches for the multicast. Because then the receiver has to join the new replicator which is closest to that particular stream. And now if sometimes we have cases that like who joins first, right? So if the source joined first, right, then it sends the PIM register message to the RP, right? And if there are no receiver that was interested to that particular stream, then the RP sends just the PIM register stop message that I don't have any receiver at this moment, so stop registering myself myself to that particular RP. In classic multicast, right, we have SPT mode, shorter path mode, right? But in SD-WAN, all the traffic always goes through the replicator. So if you enable it, it doesn't mean that like your data traffic, actual traffic will choose the best path. It always goes through the replicator. But the control packet which is being exchanged, like a type 6, type 7, type 5, those messages will be less as compared to like if you don't enable that SPD mode. But if you enable it, you need to make sure that you enable it on all the WAN edge devices in your SD-WAN fabric. The other thing which I would like to mention is that, and which I have seen in many customers, that like the multicast is not being supported or tested with the centralized data policy. So you need to make sure that whenever you are designing your centralized data policy, you only matches the unicast traffic. Because multicast is not being tested or verified with the centralized data policy. Even you have your localized QS policy, you need to make sure that only the unicast traffic is being matched in your QS policy, because even in placing the traffic into the QS, it is also not being tested with the multicast traffic. The other thing is that previously, the multicast was not supported or not tested in hub and spoke environment. Starting from 20.15 and 17.15, multicast is being supported in hub and spoke environment. But the only catch is that you need to make sure that you need to add that configuration in your CLI add-on configuration parcel, and that has to be done in your on your spokes. On your spokes templates, or if you are using configuration groups in UX 2.0. So this is the demo topology, which I would like to share with you. So let's do that. I will do a quick overview about the topology. Is that the same topology I'm using for this multicast in hub and spoke. Here we have receiver on site 1220, and we have a source in 1221, because in multicast now we can have a source and receiver on the spoke side also. So here we are just applying the centralized control policy just to make the same thing to make it hub and spoke. This configuration is being applied, and now we are just enabling the PIM and the RP configuration in the configuration parcel. So here we just enable this multicast. This is because in my case, EMEA Hub 1 and EMEA Hub 2 are the replicators. So this is the EMEA Hub multicast. This is the local replicator. And then we enable this static RP configuration. And RP is behind the SD-WAN fabric. It is on the EMEA Hub side. And this is for the dual LAN edge devices. So this configuration is same for all the spoke side to enable the PIM and configuring the RP. So once it is being done, so this is the CLI add-on which we need to add on all the spoke devices, right? So we need to configure that SD-WAN multicast, and this is the spoke. So now here we can see that the hub side, we also configure that this is the hub, it is a replicator. And now this is the WAN edge 8, right? So WAN edge 8 is the upper one, side 1221. And here we can see that the configuration which we sent through CLI add-on, it marks that this is the spoke side, right? And this is the multicast enabled. It means that the multicast PIM is being enabled on that particular side, and this side is not a replicator, because in our topology, EMEA Hub 1 and the EMEA Hub 2 are the replicators. So here we can see that the hub and spoke topology is being configured. We are receiving the default route from the EMEA Hub 1, which have the system IP 10.0.0.1, and we are just receiving those routes from the hub side. So this is the EMEA Hub 2. It has all the BFD sessions over all the devices. And if we go back here, we can see that the EMEA Hub 1 is the replicator, because the kilometer is 0. It means that it is this is the own replicator for the EMEA Hub 1, and this is for the WAN edge 7, right? This is this device 1220, and it chooses the replicator 1001, because the distance from replicator 1 and replicator 2, the closest one is EMEA Hub 1, so it chooses that one. And then we enable the debugs in order to see all those OMP route type 6, route type 5, route type 7 messages. We can see that we enable those. And then we enable those packets on the controller also to see how these messages being sent from WAN edge from the spoke towards the controller, from the controller towards the replicator, and goes to the RP, right? And then we have this the source 1221, and this is the DC source. And here we can see that we join this group 239.220.220.220, which is this. This is the receiver. And now I can see that it is sent the PIM register message. And here we can see that so we send this update message, right? And this is join XG, mean star comma G. It's region from 10.1.1.7. It is interested to that 239.220.220 group, right? And it is being received from this because he's showing the interest that I want to join that group. And this is the route type 6 packet. And then it create the ribbon entry. Remember, like multicast, we also support in the address family of the OMP. So it creates a ribbon for that multicast. And then here we can see that like this label is being created, which is for 1007. And then we send that packet towards this to the controller, and from the replicator, it goes to the RP, and we receive that. And then we receive that like the star comma G entry is being created on the hub also. And here we can see that this type 7, because it is interested to that, this is the S comma G entry. And then when the receiver received it, it sends the type 5 packet towards this controller, and the controller will send that packet towards all those, the source active message into that to all the WAN edge devices in the controller. This is the S comma G entry, and here we can see that on the controller, which we received from 10.1.1.7, and this here we see the all those packet is being exchanged. I just want to show you the route type 5, and then we have this. PT packet. This is the packet which I just want to show you. This is the source active packet which is being sent in from the OMP towards all the WAN edge devices in the SD-WAN fabric. So now we're going to talk about the service chaining. So yes.
What is the bare minimum circuit bandwidth for multicast? Is there any lower limit, like if you have 10 meg of the circuit, then
it will work fine. It all depends upon how big is your multicast fabric. So the question is like, is there any minimum bandwidth requirement in order to enable the multicast? There is no like a requirement such that like it all depends upon that how many receivers, how many multicast stream fabric is in your SD-WAN fabric. So now we're going to talk about what is service chaining. In simple words, service chaining is like if you want to have your network flow that needs to be served by some service which you introduced in your SD-WAN fabric. That is called service chaining. In Cisco SD-WAN solution, we support all three models. Long hairpin, meaning that like you want your service to be served by a couple of services. We also have a short hairpin model, and we also have an exit model. Service chaining is being supported in all models, hub and spoke, MRF, or full mesh. In Cisco SD-WAN solution, we support 16 different types of service chains, and each service chain we can have a maximum of 4 service. That is one thing. The other thing is that like once the service is being created, right, how you can steer your traffic towards that service chain. Prior to 20.13, we can only use or we can only deploy the service chaining through the control policy. But from 20.13, after 20.13, we introduce, you can do the service chaining, or you can steer your traffic towards that service chaining through control policy, through data policy and through ACL also. Through control policy, once you match your traffic, you want that I want every traffic which is being initiated from those prefixes will traverse that traffic. The data policy, you can also do that on the ACL. The only catch is that if the service is being located locally, then you can use that interface ACL, and then you can match on the service side that if the traffic is being initiated from those prefixes, you want to serve that traffic to that service which is being associated or which is being available locally into that particular site. So how does this OMP, play a role in the service chaining? So once the service is being identified, right, is being attached, then the label is being created by the WAN edge devices, and then the OMP is being used by the WAN edge devices to advertise that service towards the SD-WAN controller. The key point is that that service information is not being sent towards the other WAN edge devices. So it is only being advertised to the WAN to the controller, and controller knows that I have that service available in the SD-WAN fabric. So now the question is that how then we can, to make sure that the traffic is being traversed over that particular service. So once, for example, you use this data policy and you create the data policy and you specify that the traffic is being initiated from those prefixes should traverse that. So once the data policy is being pushed, then this data VPN label is being generated by the controller, and that label is being used by the WAN edge devices to send that traffic towards that particular service. So how that VPN label is being decoded by the WAN edge devices. So it is 83.89615. So when you do show OMP on the controller, you don't find those big numbers in the label, right? So the decoding is that. So first 83.800 is being converted into the hex. This big number is being converted into the hex, so that is like a 08x00, right? That is being informed by the controller toward the WAN edge device. So that is the service chain label. So the label you see, you convert it into the hex. So when the hex value, the first 3 digits is tell the WAN edge device this is the service label. So the next 3 digits, if you convert those hex into the decimal, this will give you the label which is being assigned or generated by the WAN edge devices. So that's how the WAN edge device knows that which label I have to use when I want to send the traffic from the WAN edge device towards the other one. And this is the demo. I just want to show one thing. So we send that policy. This is the same the hub and spoke policy we are just doing. I just want to show you that those. So here we can see that. Here we can see that because the service is being attached in the EMEA hub, right? Okay. EMEA hub, and that the service name is being assigned there, right? And the label which is being used is 1017. And then we see that this label this service is not being advertised towards the other controllers or other OMP peers. And when we send the data policy here, that label is being used. This 838695, this is the one. And when we try to convert it, right, this is the service chain number, this is the label. We try to convert it into hex, which is 803F9. This 800 is just tell that this label is for the service chaining, 3F9. If you convert it to the decimal, it gives you that label. So once that policy is being pushed by the controllers towards that WAN edge device, then the WAN edge device knows that like I have to use that label in order to send that traffic there. So that's all from my side. I don't know. Just give me. So like last time, I have some small quiz. So just to make sure that like if you understand the OMP, that is my goal. So that when you leave this room, so now you can join that and try to answer that questions. Can I after that? Only for the service training.
And why it is in hex and not time?
It's implemented in such a way because the service chain label is not being advertised by the controllers to the other WAN device. Yeah. Thank you very much. I hope you learn something new about OMP. And I will make sure that I will upload all the demo slides and demo recording into the WebEx, so you can also have that access. Thank you very much.